Lots of cool stuff in this video, in my opinion, at least. When we're looking at our enolates, we have to understand a little bit about their reactivity. And so there's a couple big things that come into play, one of which we addressed in that synthesis video, which is asymmetry. The other one to address is this idea of what base do we want to use to deprotonate. And that's a little bit more of a challenging question. So to get to that, we really actually have to address some of the basics behind this. So if we take a look, we've got three enolate formations using three different bases. For nomenclature's sake, we could go through and name each of these, and we'll go ahead and throw a little quiz question into it as well. That very first one, if we go through and look at that base, is ethoxide. The next one, very commonly known as LDA, or lithium, which is not shown in this. Typically, it's the counterion, so we don't worry about it as much. Diisopropyl amide. And then the last one would be hydride. Also, typically, whoops, as I start to use the wrong symbology there, sodium hydride is almost always how we go through and see that. So these are three very commonly used bases, and we're going to introduce or reintroduce this term of stupidly strong. All right, so when we look at these bases, what we want to be considering is what makes them strong or weak. And the base that you may be more familiar with, because you've seen it a whole bunch, would be like hydroxide. So if we're going to follow the pattern that we're seeing, at least for the ethoxide underneath, really the difference between ethoxide and hydroxide is that instead of it being carbon, we're looking at an ethyl chain or a 2-carbon chain. Well, how is that going to affect its reactivity? Ultimately, as far as base strength, it doesn't do a whole lot because there isn't a huge difference between carbon and hydrogen. But what it does do is a solubility difference. So ethoxide ends up being a little bit more soluble and agreeable to organic solvents because you have that carbon chain as opposed to the hydrogen, which means very aqueous based. So yeah, not a huge difference in acidity. And we could see that difference in acidity if we went through and say used pKa's. Yeah, so if we were to go through and look at, say, the pKa's for ethoxide, if we went through and looked at hydroxide, you'll notice it does not have a pKa in this category because that's the base form. The pKa of its conjugate acid, being H2O, comes in at 15.7. So really almost identical, not a huge difference. And we could predict that kind of lack of a difference based off of it being a negative oxygen. Well, what happens if we look to the next one? We're looking at nitrogen. So now we're at least changing the element. What's the difference between nitrogen and oxygen? Electronegativity. Okay, so based off of electronegativity, we would expect the oxygen would hold that charge better than the nitrogen, which means the nitrogen should become, more basic. And we can see that when we go through and look at the pKa, because its conjugate acid is much less acidic. Okay? And that kind of balance that you learned in 152 can be challenging, so be aware of that. And since its conjugate acid is less acidic, the base is more basic. The way that I would like to go back and think about that is that if we look at what a base is, a base needs to donate those electrons. If we compare oxygen to nitrogen, oxygen being more electronegative is holding its electrons. The base needs to donate them. Since nitrogen is less electronegative, it is more willing to share that pair of electrons than, say, the oxygen, and that makes the nitrogen more acidic, or more basic, sorry. And what we're using to evaluate that would be, and I would hesitate to call them my rules, but the organization system that I've used for evaluating reactivity. We move charge, size, and then in this case, electronegativity, or the symbol that I use for it is chi. That's then followed by resonance and induction. Okay, and so I bring those up so that you remember them because you need to. And then the last one would just be because of course I can't swear, we have to be a little bit more careful about nuancing the differences there, okay? So what happens then when we move to hydride? Well, hydride becomes a little bit more tricky, and if you looked at the kind of the pattern behind each of these slides or each of these sections, you might have seen a little gray box, and you don't see that gray box for the hydride. And the reason being is that hydride, or its conjugate acid rather, is so unacidic that we don't have a pKa for it. What does that mean? That means that the base form is exceptionally basic. So hydride is very, 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 very basic, right? How basic is it, or how would we have predicted that base strength? Well, that's where we would go through and use our rules. The charges were all the same in each of these cases, size. The very second rule on the list, size. Okay? Hydride is so small, it can't stabilize the electrons. And that's why hydride becomes a stronger base. So when we're looking at these, I would argue, because hydroxide we consider as a strong base, that we need a new definition, okay, or a new terminology. And that these bases, as I box in the non-bases, the LDA and the sodium hydride are so much stronger of a base that we need to give them a different name, okay? And this is where, yes, the spelling is intentional. I've referenced these as stupid strong. Okay, and we'll see that pop up again and again and again because it really does change the reactivity of what we're looking at. And so those are stupid strong bases. Because they're stupid strong, certain things change about the chemistry in predicting. Okay, so that's what we need to be aware of when looking at these. Other things to consider. When we look at the reactions shown here, you'll notice that the arrows in between each of these reactions is different. For the ethoxide, it's an equilibrium that favors reactant, which is important to note. Okay, so we don't form a large concentration of the enolate. When we move to the LDA and the sodium hydride, those aren't equilibrium. They solely favor the product. So there's a significant difference in the base strength there that really only projects that reaction one way. Okay? Said another way, when we use ethoxide, the reaction is reversible. When we move to LDA, it becomes irreversible. And there's a couple things that contribute, or really, we'll start with one. The pKa difference is really what makes those irreversible. But there's some other aspects that come into play, particularly with the hydrogen. Okay? The H2 gas, as a gas, it bubbles out of the reaction. Can the reaction reverse if the reagent isn't there anymore? So hydrogen gas is so irreversible, or sodium hydride as a reagent is so irreversible because that hydrogen bubbles out, we don't even have the species necessary to reverse the reaction. And this is going to become really, really important when we consider the concepts of kinetic and thermodynamic, which hopefully you've now seen that video about kinetics and thermodynamics. And so what makes one better than the other? Well, that strength changes that reversibility aspect, which then potentially changes which product we get, be it a kinetic product or a thermodynamic product. So the one better than another has a lot to do with what we're trying to do. Okay? Where's our end goal? In a lot of the cases that you're going to be seeing, you'll be given a reactant and product, and you have to predict which base to use, because if you pick the wrong one, it doesn't make that product. Or you could be given a reactant and one of these bases and then told to predict the product. You now again have to use that information to decide what's going on within that. When it comes to synthesis, we'll see this pop up again when we get, I'm going to say, the end of the next unit, and then fairly significantly in the third unit, looking at what bases we're using when we go through to run these reactions. Okay. Oh, this is a fun little one. For sodium hydride, is it big or small? Okay. Remember, the bigger the structure is, the more likely it acts as a base because it can only access the hydrogens on the outside of the molecule. The smaller it is, the more likely it can act as a nucleophile. So when we look at sodium hydride, is it a big base or is it a small base and now potentially an issue as a nucleophile? Turns out it's a really, really big, massive base. And that's a really weird kind of observation because when we look at it, it's H minus and we're saying it's reactive because it's so small. It is so small that the connection between the hydride and the sodium is fairly constant. Okay? And that in most solvents, those don't separate well, which means when we're looking at sodium hydride as a reagent, it's a multi-phase system. You've got the sodium hydride as a solid. The only place it interacts is on the surface of that solid. That's actually a pretty small surface area. Sodium hydride acts as a fairly large base, which is kind of interesting. So, enolate chemistry, we need to make it happen. So we've got two structures here, and in class I would have you go through and try and provide the mechanism for the formation of the enol or the enolate. In this case, we'll look at stages of it. But actually, it's fairly straightforward. I think we'll probably do both. So what we want to go through and do is make either the enol or the enolate. Since the basic pathway tends to be the most common and easiest to see because of those charges, let's go through and look at what happens if we just used a strong base. Right? So there's a negative charge. That base could remove the hydrogen. The electrons could bounce up here, which would cause those electrons to shift, and we would result in a resonance stabilized enolate. And there's our resonance structure. Whoops, helps if we have that double bond there, where the electrons shuttle back to the middle, and we could say, well, we've got this resonance. Well, cool. What happens if we did it with the other structure? Right, well, in the other case, the base still comes in, attacks our acidic hydrogen. We're going to see a question on that pop up in a second. Double bond, oxygen, should be singly bonded. Negative charge, hydrogen. We could go back and do the resonance and show our structure, right? And we have our enolate. So the question that would come out of this, right, we've got two pathways that we could go through and do this. What base do I need to use for each? Right? That question can be kind of a bit loaded at this stage because you aren't really familiar with why does it matter. Well, first and foremost, if we think kind of green chemistry, which is a good thing to keep in mind in synthesis, we want to use the weakest species that gets the job done. Because if we use something that's overkill, we could potentially run into a lot of other issues. For instance, if I want to put a nail into a board, I can use a hammer. I can also use a wrecking ball because a wrecking ball has enough mass, right, that it could knock the nail into the board. But the wrecking ball would probably also break the board and my hand if I was holding the nail. So I want to be careful to choose the reagent that is weak enough to do exactly what I need it to do. Which means when I look at these two reactions, what base should I pick? And we've got three: ethoxide, LDA, sodium hydride. So for our, we'll call it our red structure, what base should you use? If you picked ethoxide, then you would be correct, right? And let's call it our purple structure. What base did you pick? If you selected ethoxide, then you were wrong, actually, because it wasn't ethoxide. You'd be picking LDA or hydride. Okay? Either one would work, and so if you picked LDA and got marked wrong, tough. Don't stress. Why the difference? Well, that difference stems from the fact that the red one is more acidic. Why is it more acidic? Then the purple one, which is less acidic, well, it has to do with resonance. The red one has an additional resonance structure. That increase in resonance, in this case, because sometimes an increase in resonance is bad, depends what it's doing, makes it more acidic, okay, or more willing. Since that's the case, I want to use a less strong base. So we need to be thinking about that when we go through and run our reactions. Use the weakest species that will get the job done, right, as you want it to. Right? Before we advance on, I did kind of hesitate because there was a question I was going to ask. It is incredibly common with this structure for students to go through and remove what I'm labeling as the green hydrogen. Okay? This is of critical importance because you will likely make this mistake, because when you see this structure on an exam, what you're going to see is actually this. And when you see it drawn that way, which hydrogen do you think you should remove? Probably going to lean towards the only hydrogen that's shown. That hydrogen is not acidic, right? Nothing about it is acidic. So what you should be able to go through and do is remove that hydrogen and explain to yourself why it is not acidic, okay? And to that end, I've even got a question here that we'll pull up and test you on. Okay, and so with that, hopefully we're good. And we could look at pKa's to evaluate those acidities. Again, we were able to predict that without looking at the pKa. We don't have to do 152. We have to understand something about resonance and charge and all that fun stuff. And we can predict these things without having to draw in the mathematics. If you want to draw in the math, that's fine, but I don't. Get out. That's kind of mean. Stick it out, but keep finding some other numbers. So how do we use all of this now in conjunction with unsymmetric or asymmetric ketones? If we look at that structure, we're definitely going to be doing an equilibrium. And you'll note already that I've got two different arrows coming out of this. And the reason we have two different arrows coming out of that is because we have hydrogens that I'm labeling as blue that are acidic, and we also have this hydrogen here, or sorry, red that are acidic, and now blue that is acidic. Those are at the alpha positions, and those hydrogens could be removed. Right? Well, how do we know which one's more acidic? It's a bit of a crappy question. A lot of that's going to depend on what the base is you're using. Okay, so let's first look to see what would happen if we removed a red hydrogen. We'd form the negative carbon out there. We'd have that. If we looked at the blue, we would have the negative carbon there. And you might go through and evaluate differences in stability. And by might, you should. Okay, and hopefully what you would say is the red one is more stable because it has the negative charge on the carbon that is less substituted, and that's good. But don't these have resonance? Couldn't I have drawn the resonance structure where those electrons shifted down into the ring a little bit, which then kicked out electrons onto the oxygen? That would then put the negative charge on the oxygen. And if I did it for the blue structure, now what happens? Negative charge out onto the oxygen. Do you still maintain that the red structure is the more stable one? Hopefully not, right? Hopefully you're now acknowledging that the blue one is more stable. When we evaluate the stability between these things, again, we start with charge. It's the same in both cases, so not relevant. We could then move to size. It's the same in both cases. Well, now it's the same. We could then move to electronegativity. Wherever there's active electrons is the same in both cases. We could then move to resonance. They have the same resonance. This is starting to get a bit obnoxious. Induction, oh my goodness, that's also the same in both cases. And really what we have to move down to is into that kind of carp moment. which is instructive because it's going to allow us to evaluate that difference. And really what we're evaluating is the pi bonds. The pi bonds are different. The red one is less substituted, and the blue one is more substituted. A more substituted pi bond was more stable than a less substituted pi bond, which would suggest that the more substituted should be the one that forms. But when we looked back and looked at the intermediates, didn't we say the red one should have formed? This is where we introduce the kind of dilemma of kinetic versus thermodynamic as far as these kind of reactions can shift and move around on us. And that's why we have to be careful when we think about the choice of base when we go through to evaluate these things, because the choice of base is largely what's going to contribute to dictating which pathway we go. Okay? So, major product, it's a question. We have to see what we're going to look at. We have to look at those conditions that are going to drive our reaction one way or another. Right? This is why we have to think about our energy diagram and build this out. And we have to understand what's happening at each of those stages. I did have to throw in the hydrogen here in this case. That hydrogen was thrown in to get us to the enol form, so that the enol gives us an actual structure that isn't a resonance structure to help us with this. But if we were to go through and do this, we could start with our reactant floating somewhere in the middle. We move to our intermediates and then our products. If we look at our intermediates, we have two. Okay, we will call it a red intermediate and a blue intermediate. And if we looked at intermediate, regardless of what color it is, begins with I. The red intermediate, we said, was higher in energy because we put a negative charge on a more substituted position. The blue one, a little bit lower. Both of them should be higher in energy than our reactant because they're charged. We move across to the product, we get a red product and a blue product. Both of those, it's a little bit questionable there, but let's just go ahead and drop those as lower in energy than everything because we've got space ultimately for it. But realize that it is higher in energy because all of our equilibrium arrows are pushing back towards our starting material. So if we were to go through and do that, we would put our red product low and then our blue product a little bit higher. And if we drew out our energy diagram, well, that's not that big a deal. Oh, there's our issue. That point is what's going to be the crux of which product we get. Where do we see the pi bond ultimately situate? And that's going to dictate where our nucleophilic chemistry is going to come from. Right? How do we decide which one it is? Well, we have to understand something about which product we've got. The blue one, I would argue, is the kinetic product. Okay? And it's going to kinetically form first because the activation barrier is the lowest. The red one would be our thermodynamic. And it would be thermodynamic because the product itself is the lowest in energy. Okay? So this has to do with our product. And the kinetic has to do with the activation barrier. The kinetic one will always form first. Okay? And that's where things become a bit challenging. So if it always forms first, shouldn't we always see it? Well, a lot of that is going to depend on this barrier, or rather, this barrier. Okay? That barrier now becomes a critical importance. That is the activation energy for the reverse reaction. Okay? If we heat up the reaction, do we provide enough energy to clear the reverse? If we have enough heat to clear that reverse, the kinetic product will revert back to the reactant. Some of it, even if it's a small amount, will transition to the thermodynamic. What becomes the problem with the thermodynamic? Its reverse barrier is so much higher that that reaction is irreversible. So a lot of this comes down to the reversibility of the formation of that product. That reversibility has a lot to do with the base and temperature of your reaction. If you use a stupidly strong base, it is an irreversible base, which means that step that we're so concerned about for the kinetic, that activation barrier becomes massive if using an irreversible base. So that irreversible base means we get the kinetic product. If instead we used a reversible base, well, that kinetic product can revert back to the reactant. That reactant will eventually form the thermodynamic, and the thermodynamic will always be irreversible, right? Or at least in comparison to everything else, more irreversible than everything else, and therefore the primary product. So a lot of this is going to play or bounce back and forth between the interplay of the temperature of your reaction and the individual reagents used. Okay? I'm kind of hoping that I have this nicely drawn underneath. I kind of don't think I do. I kind of think where we're at is the end of the video, but we'll see what pops up here. Yeah, so both are major products. It just depends on the conditions. Right? So for our kinetic products, the kinetic products tend to favor cold and short times. They also tend to favor LDA and sodium hydride. Before you get all jumpy on, oh, I'm just going to memorize LDA and sodium hydride, we could change the base to another or different stupidly strong base. You should be able to acknowledge what makes it stupidly strong. It has to be similar to LDA or sodium hydride. Okay, so don't just memorize the reagent. For the thermodynamic, we're looking at hot. That's in the name, so that helps out. Usually long times, because what we're doing is pushing for an equilibrium. So we have to push all the way until we get there. And then we're using sodium hydroxide. Okay, or ethoxide. We're using some kind of oxide base. The oxide bases tend to be reversible, and the LDA and the sodium hydride tend to be irreversible. Could we encounter a situation where we mix it up, say use hot, short time LDA? Yeah, that's really just kind of being a dick and asking for you to predict out and explain what you should get, right? Which is kind of just a mix of everything, right? So it is a complex concept, but it is one that we're going to be constantly coming back to. This is why I had you watch the kinetic and thermodynamic video already. Theoretically, you've seen it, and this is where it shows up again. We will see these enolates. So before you're like, oh, I'm just going to not worry about it, we will see these exact same enolates, both the balance of kinetic and thermodynamic, show up again and again and again and again, which means you really do need to understand this difference. It's kind of like mercury versus, or the mercury addition of H and OH, or just a straight up water acid addition of H and OH. They do the same thing, but differently, which causes a different result some of the time. So if you understand the underpinnings for why they're working, you can get to those answers a little bit better than someone that just memorized the answers. And yes, we will see that when it comes to any test. Right? And with that, I think we are actually done with this entire unit, but we're going to hit next just to see what happens. Oh, yeah, I forgot. This summarizes, admittedly, this was built for a different sequencing of materials. So there's some reactions on this that you don't need to know right now, but you will need to know them by the end of the semester. And so figured showing you the spider diagram now might come in handy. To give you an idea of some of the reactions we've talked about, we've looked at this one, this one, this one. We mentioned it, though I didn't name it. I did name the haloform reaction. We haven't done any of the aldols, so we don't need to worry about that. or the Claisons. So we're really just seeing the top half, and even with the top half, we haven't done all the way. So this one we've done, but we haven't done these. Okay? So hopefully that gets you an idea of where we could be going and helps you plan for the rest of the semester. With that, thank you for listening and making it all the way through this Unit 1. Hopefully it had some interesting points. I know it did have some weird organizational, issues, but hopefully you did find it interesting. And with that, thanks for listening. Use your model kits. Or when in doubt, draw it out. That's what we're going to end with. When in doubt, draw it out.